Hi, Jam. So, in the last class, we learned about titration curve and charge calculation, and we also learned different amino acid structure. Okay, so today we will see how this amino acid actually arranged to form a protein. That's quite important. And before diving into that, uh, we will see one question here, and that's actually asked in IIT Jam 2019. Okay, so the question was that uh, suppose I am giving you four option. I am giving you W, F, I, K, L, S, P. This is one peptide. Now A, G, V, L, P, S, R. This is another peptide. C. This is W, I, K, L, Y, G, A. This is another peptide. And then the L, I, K, S, P, Y, G. I am telling you which of the following amino acid will show highest A280 value. That same question was asked in IIT JAM 2019, right? Now, if you want to solve this kind of question, you have to think which amino acid is responsible for absorbance at 280. Okay. Now, for A280, the responsible amino acid is mainly tryptophan and tyrosine because these two amino acids are aromatic in nature and also they absorb strongly at 280 nanometer. And another amino acid that is mainly absorbed at 260. Okay, but also it will absorb some at 280. Okay, now tryptophan and tyrosine, these two are mainly related to A280. Now we have to see each of the following peptide, how many tyrosine and tryptophan residue are there, and also you can calculate phenylalanine here as well. So aromatic amino acid. So because in aromatic amino acid, what will happen? There will be some electron delocalization, right? So if something is coming, then it will go like that. The resonance will happen. Okay, and it will show some absorbance. Now here there is one tryptophan, one phenylalanine, right? I am writing two. Here that nothing is there almost, so that's 0. Here W, Y, F 3 is there, and here only Y 1. Of course you can see here in option C there is 3 aromatic amino acid. That means the C will show highest absorbance at 280. Now another kind of question is to ask about the molecular weight of peptide. So how you can calculate molecular weight of amino acid? Suppose this is glycine, the simplest amino acid we are taking. Now you can easily calculate the molecular weight of glycine. So the thing will be C2NO2 and H5. Now 16 into 2 plus 14 plus 30 16 into 2, sorry, it will be 12 into 2 plus 5. That means 24 plus 14 plus 32 plus 5, that will be 75. So the amino acid of glycine, uh, its molecular weight is 75. Similarly, you can calculate for alanine, arginine, histidine, every amino acid. But suppose I am giving you one stretch of 100 amino acid residue. At that time, you can't individually calculate, right? Suppose this is glycine, this is alanine, this is valine, this is proline, this is glutamate, this is aspartate, histidine, again glycine. You can't calculate for every amino acid. Then your 3 hour will be ended for sure. So what you can do, in generally the average molecular weight of amino acid is taken as 128. Okay, Suppose you calculate for 20 amino acid molecular weight, then you just average it. Okay, but as in peptide, right, there is some peptide bond is here. I will explain what is peptide bond. Okay, so due to the peptide bond, the average weight is minus 18, that is 110. Why this minus 18? So in what is happening in peptide bond here, one water molecule is releasing, and water molecule contain 18, right? That's why 110 Dalton. So if I'm telling you 100 amino acid is there, the molecular weight will be 100 into 110. That means 11 kDa. Okay. Now there are multiple kind of question can be possible. Suppose I am telling you one question that uh, you have you have 50 glycine and uh, it is forming a uh, disordered structure disordered structure or anything. Now calculate molecular weight of this 50 amino acid stretch. How you can do that? So 50 amino acid, that means how many 50 into 75, you know the exact molecular weight of glycine. Here you can't put 110, right? See, 50 into 75 minus, suppose there is 4 amino acid A, B, L, K. In 4 amino acid, if it's linear, then there is 3 peptide bond. 3 peptide bond, right? That means if n number of amino acid is there, that will be n minus 1 peptide bond. Peptide bond. That means here you have to subtract, okay, 49 peptide bond into 18. If you do that, you can easily get the molecular weight of 50 amino acid stretch, right? And if similarly I am telling you that it is forming a linear, okay, if I am telling you the same question but I am mentioning that 50 amino acid is forming circular peptide, forming circular peptide, at that time what will happen? At that time 50 into 75 minus 50 into 75, because suppose A, B, L, K, and again K will be connected to A. That means there are 4 amino acid but there is 4 peptide bond. So for n amino acid there will be n peptide bond. Remember, first circular peptide, right? This is third question. Or people can ask you like that. Suppose if there is 20 different kind of suppose if there is 100 amino acid and if the 100 amino acid is forming one circular peptide, what will be the molecular weight? You can easily calculate it. Okay, so you have to remember that whenever there is linear peptide, in that case the peptide bond will be n minus 1, and if it's forming circular and for n amino acid it will be n peptide bond. Simple thing. Okay, now we will see about peptide bond, like why we are just subtracting 18, right? Now it's the perfect time to understand the peptide bond. So few information about peptide bond is that okay, I will tell you later, but first let's understand what's peptide bond. H3N positive CH R1 C double O, sorry, we should do it in a different way. Okay, so here it is carboxyl group, and now again there is H2 or H, NH or H2. Here it's H2N. Let's see for better understanding. Again R2 and then COOH. Now what will happen here? There is two amino acids, so there is COOH and there is HNH. Now what will happen here? The OH and the H, that will make some hot water and it will be released, and because of that it will form some peptide bond. So CH R1 CO N H CH R2 COOH. Now champ, just observe here the particular region CONH. So if you see it, this is CO and N and H, nothing else. So this CONH, this amide bond is called peptide bond. So this is nothing but amide bond. Sorry, I can't say it directly, amide bond. That means NH2 and the COOH, they are reacting and they are releasing one molecule water, and that's known as peptide bond. But remember, the peptide bond is not spontaneous, because just assume two unknown people are there, right? But these unknown people don't know each other, right? Like how they can start some conversation? So sometimes we need some third person who will just make the path easy. So like that, ribosome used to do the same thing, and there are a lot of GTP energy expenses. So this peptide is basically non-spontaneous. Non-spontaneous. Delta G equals to plus 21 kilojoule per mole. Okay, that means as delta G greater than 0, that's why it's non-spontaneous. Okay, now we'll see few characteristics of peptide bond. The peptide bond seems here it single bond only, right? But if you see it carefully, what will happen here, that the here and here there will be there will be resonance. The lone pair electron of nitrogen will come here and that double bond will go to there, and then what will happen, that will be uh, like that, and NH. So there is some partial double bond characteristics of the peptide. So this peptide is partially double bond, partial double bond, double bond. In general case, there is C alpha, it is CO, and then N H, and then again C alpha. That's the case. Now here this C and N bond, that is partially double bond, partially double bond. How we can get to know that? Its distance is 1.33 angstrom. In general, the CN single bond length is 1.49 angstrom. CN double bond is 1.27 angstrom. So the peptide bond CN length is in between them. That means it partially double bond. We know that in case of suppose single bond, the bond length is maximum. For double bond, triple bond, the bond length is used to decrease. So here, as it's partially double bond, that's why it's intermediate between single bond and double bond. Okay, this is one thing I should remember. Second thing is that here all this atom in a single plane. Okay, so point number 2, all atom basically 6 atom. So all these are in a single plane. This C alpha, CO, CONH, C alpha. So 1 2 3 4 5 6 atom are in same plane. That's really important. So partially double bond, that's non-spontaneous, and all these six atoms are in same plane. Now this is C alpha, this is C, this is O, this is N, this is H, and this is again C alpha. This bond is so what will happen? There will be some rotation of this bond, right? And because what will happen? So suppose this is one amino acid and this bond is fixed. Now that bond will rotate. Okay, so the rotation between N and C alpha, that rotation is generally termed as phi. So, and the rotation dihedral angle between C alpha and C is generally mentioned as psi, and the Cn is mentioned as omega. So phi is between N and C alpha, psi is between C alpha and C, and omega is between N and C. Remember this thing. So the omega value 0 or 180. So 0 for cis, 180 for trans. In maximum peptide bond, so it's 180. We know the concept of cis trans, right? Suppose there is two bond here. In that case, the most priority group, suppose H, H, Cl, Cl. This is called cis. The same thing, C, suppose Cl, suppose Cl here, H and H. That's called trans. Okay. In case of amino acid, what will happen as cis trans? Suppose this is C alpha and this is H R, and now CO in H, now C alpha HR, that is trans, and cis, that is C alpha HR CO NH C alpha HR. Similar in same projection, that is called cis. Cis is sterically not favorable, trans is most favorable, and proline generally introduced this cis from trans to cis. That's why sometimes proline is considered as the helix breaker. We will discuss this later. Okay, so that's the basic concept of the peptide bond. Now, what we have to see how this phi psi angle varies according to different uh, secondary structure. Okay, but what is secondary structure? So suppose just as right now you have multiple monomer. Just imagine you have a amino acid monomer. There's nothing attached. Now you attach them one by one like bead. Okay, necklace kind of thing. Okay, one by one. So that is called primary structure. Primary structure is nothing but amino acid stretch, and after that this stretch is, it can't be like a rod like thing, right? It has to take some conformation for its spatiotemporal arrangement of the group, functional group, because it has some bulky group, it has some hydrophobic hydrophilic group. We have to place them, we can't simply directly project to outwards, right? For that purpose we need secondary structure. Okay, in secondary structure generally we have seen one is alpha helix and another is beta sheet. And after secondary structure, what, so this is alpha helix and this is beta sheet, parallel anti-parallel, a lot of things are there. Okay, and after that this is quaternary structure, third degree structure. Here the protein is actually folded, and one protein, folded protein, we have multiple domain, and multiple domain can consist of alpha helix, beta plated sheet, some loop, everything. So quaternary structure is basically alpha helix plus beta sheet plus coil plus loop, everything. And then suppose if four subunit, there is multiple subunit are interacting each other. So suppose that's one subunit folded, that's one subunit folded, that's one subunit, that's one subunit. At that time, this is called quaternary structure or fourth degree structure, like hemoglobin. Okay, you can also think this is amino acids are words. Okay, so suppose I'm telling you these amino acids are words. This is amino acid. Now primary, that's the sentence. Sentence is the primary. And then third, secondary is the paragraph. Paragraph, that's secondary. And multiple paragraph, that's a chapter. Multiple paragraph. And from chapter to book, that is fourth degree. So words to sentence to paragraph to chapter to book. Okay, got it? That's a similar thing happened to amino acid. So we are already familiar with amino acid stage, primary structure, amide bond formation. That's here peptide bond formation happened, right? Peptide bond formation. Okay. In secondary structure, how alpha helix and beta peptide sheets are formed, we'll see. And before that, I just want you to know a little bit about phi and psi value. Okay, we can see it later as well. Now, alpha helix. So through structure, through the sequence, you can say that whether that will form alpha helix or beta peptide sheet. There are a lot of tools are there. Okay, and like AlphaFold, Rosetta, so that you can predict the structure quite accurately, and then you have to validate it. Okay, now okay, let it that kind of things are called alpha helix. It's helical, coil. Here, few things you should remember. First thing is that in alpha helix, there is some hydrogen bond formation between nth and n plus fourth amino acid. That's a very fantastic question. So suppose n is there, n plus 1, n plus 2, n plus 3, n plus 4. N, that's CO. Okay, this CO will make some bond with that H, NH, sorry, hydrogen bond. Now, that hydrogen bond is actually working as a driving force to hold, to particularly giving a shape of a protein, right? It's providing shape of a particular protein. And the second thing is that all the side chain, the side chains are projected outward. Okay, and here there is backbone. Suppose here it is a CO and here it is the NH. Okay, this is the H. Now there is bond. Now again this is O, this is H, that is hydrogen bond. Again that's O, and then here H, again hydrogen bond. It's like that. O, H, hydrogen bond. It means N and N plus 4, right? So yeah, in alpha helix you have to remember when the amino acids are taking this helical turn. Okay, the distance between two amino acid is 1.5 Armstrong. So I'm writing that's the distance between two amino acid. Okay, and in a particular okay, so that one is called pitch. Okay, so in a particular pitch, in particular turn, okay, in a particular turn, there is 3.6 residue per turn. Okay, and that means one turn 3.6 into 1.5, that is 5.4 Armstrong. One turn the distance between two turns are 5.4 Armstrong, right? And many more things are yet to come. And there are some amino acid that prefer helix and some amino acid breaker. Okay, among breaker you can say proline and glycine. This proline, due to its rigid structure and the amine group, okay, it can break the helix. And also the 5 value of proline is constant, it's minus 60 degree. That is enough to break the helix. And also multiple amino acids are there, okay. And beta peptide sheets, so they are sheet like of structure. This is anti-parallel, you can form some parallel, that means the direction of will be same, right? So whatever today we will do, we will see phi and psi angle for this kind of structure, and tomorrow we will continue with the mathematical example of alpha helix and beta plated sheets. Different kind of question can be asked from there, okay. Which amino acid is helix breaker, which amino acid is helix maker, okay, all these things. And what is loop, what is bit turn, what is the difference between loop and turn, different kind of turn, alpha turn, beta turn, gamma turn. In case of beta turn, different kind of like type 1, type 2 beta turn, okay. Now I am giving you a reminder, this is C alpha, this is C, O, this is N, this is H, and again this is C alpha. That is called phi, that is called psi, and that's omega. Now I am writing here, that is the secondary structure here, and then this is the phi value, this is psi value. Now anti-parallel beta plated sheets, I am indicating with that anti-parallel beta plated sheets. The phi value is around minus 139 degrees and 9 degree, and sorry, and the psi value is plus 135 degree. Okay, and parallel beta plated sheets, that is minus 190 degree, 119 degree, and plus 113 degree. Sorry, this is angle, dihedral angle. For right alpha helix, that's the minus 57, minus 47. For left-handed alpha helix, plus 47, 57 plus 47 degree. For collagen, that's minus 53 degree plus 153. Okay, here the catches is the phi and psi value, sorry, I should tell it earlier, that varies from 182 minus 182 plus 180, but it can take any angle because this is not sterically favorable. So which angle will be sterically favorable, so that a particular secondary structure can be formed? That was first given by Professor G. N. Ramachandran. And he established one department in ISC Bangalore, that's Molecular Biophysics Unit, and he is the first chairman of that department. It's a fantastic work by Professor G. Ramachandran. So that will tell you that which angle are allowed, okay, and his plot is known as Ramachandran plot. The Ramachandran plot is basically like that. In that angle, that's phi and that's psi. Okay, now he mentioned some area of that Ramachandran plot. At that uh, area or at that particular angle, secondary structure is possible, and in the rest of the area is there is some constraint in formation of secondary structure. So if we plot it, so for anti-parallel beta plated sheets, that's minus 139 plus 135, minus 139 plus 135, and in that area this is anti-parallel. Now parallel beta plated sheets, minus 119 plus 130, minus 190 plus 130, that's similar like here. So that is parallel beta plated sheets. Then collagen, minus 53 plus 153. Okay, minus 51 plus 153. That means it's around here. Collagen, I'm writing C. Now minus 57 plus minus 47, that is here. This is alpha R. Plus 47 plus 57 plus 47. So 5 plus 57, 5 plus 47. That's here alpha L. So like that, if someone give you the Ramachandran plot and they can ask you that at which quadrant you will find left-handed alpha helix, at which quadrant you will find right-handed alpha helix, then you can easily tell through the Ramachandran plot. And in Ramachandran plot, the maximum area is allowed for glycine because glycine has least side chain, and sterically it's not that much steric hindrance is there, right? So for that purpose, glycine is allowed across the Ramachandran plot, and for glycine, like it will be like that something, all of region will be accessible, but most of the uh, region are not accessible for proline. Okay, so glycine and proline, they're inverse in Ramachandran plot. Okay, so tomorrow we will see different mathematics from alpha helix and beta plated sheets, and uh, I request you to please remember this thing, because in I think IIT Jam 20 they asked some question that in case of parallel beta plated sheet, what will be the phi and psi angle, or they can ask you if the distance between two amino acids is 7 angstrom, then what will be the phi and psi angle in some random way. Okay, okay, see you tomorrow, and tomorrow we'll discuss more about secondary structure, protein folding, and Finson's experiment, and Levinthal paradox. Okay, bye bye.